Okay, so the first part of today, we're going to be talking about special functions, which are piecewise functions, and part two is going to be absolute value. And I think that, sometimes if you're trying to write an expression or a function and you want it to kind of model your direct situation, you've got to be a little creative. Okay, and so, sometimes it's pretty straightforward. We're like, oh, if you're going to buy fruit at the grocery store. Okay, based on the number of pounds you purchase, there's going to be a direct cost associated with it. And so they put whatever's in your bag or fruits or vegetables, they put it on the scale, and based on how many pounds you buy, the cost goes up. Okay, so if you buy 1.7 pounds of apples or cherries or bananas or whatever you're doing, it's going to have a specific value. And so that's going to be a continuous function. And you can see that a linear model makes sense for that. Well, there are some things that, quite honestly, that doesn't make sense. And so if you think about it, if you go to the movie theater, okay, and so if your age is going to be the input and the cost of how much you pay for a ticket is going to be modeled there. Well, the thing is, they don't ask you to jump on a scale or ask you your exact age in days to give you numerically your value of your ticket. They're going to say, okay, if you are up to maybe 5 years old, making this up, maybe it just costs you $10 or $5 to go to the movie. Okay. And so 0 to 5, you pay $5. Okay. What if a student price might be 5 till say, probably till like a senior discount. So basically if you're a student, maybe there's a very through 20. Okay. Pretend they have a student rate. Okay. Assuming that you're in college or something until you're 20. I'm like, oh, let's just charge them $10. So now the thing is, you don't pay two different costs if you're 5 years old. So if you're 5 years old, you still get the lower rate. But after that, okay, once you're 6 and older, you're going to pay the bigger rate, and maybe, people who are 20 to say 65, okay, senior citizens pay another rate. And then maybe senior citizens go back down to another value. Okay, so what I want you guys to think is, sometimes it's not just like, hey, I'm 7 years old, I'm going to pay a different price than if I'm 8 years old. It's actually the same values for whole values for X. And so I want you guys to see this graph is in pieces to model the situation of the different domain values, the X values, the inputs, and based on those values, you're going to follow a different code. Okay. And so some of the graphs that we do today, as you can see on the notes, they're going to be more like going uphill or going downhill, because there is some increasing, but they are different from each other. And so there's different pieces of graphs. Now, the other thing is it's going to be a function. And so each input should only have one result. Okay. So make sure it passes the vertical line test. And notice at 5, I don't have two different results. One is filled in and one is open. And so if you ever have it failing the vertical line test, we're writing piecewise functions, there should be a specific output for every input value. Okay, so we're going to do this from a couple different perspectives. Okay, so the first perspective is, let's just kind of look and say, hey, what is a piecewise function? A piecewise function is going to be, let's see if I can get this to move around a little bit. A piecewise function is a function, so it passes the vertical line test, and it has two or more expressions to model the relationships there. And so each expression should be defined for a specific interval or X value that you input. Okay, so for every X value that you try to figure out, you can look at the graph to say, what is going on here? And so, here's something kind of like my cost for the movie. So you're like, okay, if you're between 8 and 12, okay, greater than or equal to 8 but less than 12, you're going to pay maybe $28. Okay, if you're between 12 and 16, if you input those X values, well, then your resultant answer is going to be 24, and so on and so forth for the 12. Now here you get a little bit more creepy. If you plug in an X value that's less than 2, the function that models this best is going to be this line. If you plug in X values between here and here, you're going to do this. And if you plug in X values that are greater than 5, you should follow this function. it's kind of like, I say this, and I don't know if this helps or hurts. I say, this reminds me of when you put away groceries. If something has to be very cold, well, then when you put away groceries, you put it in the freezer. Okay. If it can be at room temperature, well, then you put it in room temperature. Okay. If the temperature has to be whatever temperature ratings is in a refrigerator, well, then you put it in the refrigerator. Okay. And so you have to read the if, say, well, if I have an X value that happens to be 3, well, then you plug it in this function. If you've got something that's got to be cold, like milk, okay, 3, well, then you plug in 3 here and you see what you would get. You double the X, which is 3, 6, and add 4 to it. And then you would get your resultant of 10. Okay, so based on whatever X is, you got to read the ifs to say which one applies to it and then plug it in to see what the output would be based on what you plug in. And so I will ask you a couple of things. I'll be like, okay, well, how about if I say, here is a piecewise function, and it gives you the ifs. If you have an X value as an input that's less than or equal to 2, well, then you plug your X value into here and get your resultant answer. Okay, so the function is 2 different values based on what you would plug in. Okay, so based on what kind of grocery, if you got laundry soap, you don't put that in the freezer. Okay, well, you could, but you normally put that in your laundry room. So you look for the ifs. It's like, what do I have? What does it need? Where does it go? Based on what the if is, you plug it into the related function. You put it away where it goes. And so if I say, okay, it says evaluate this when X is -2. So if you do f of -2, I don't know what I'm writing there. Okay, f of -2, what you would say is, okay, well, if I plug in -2, okay, read the ifs. Which one does it fall in for the X? Okay, if you plug in a domain value that's -2, well, the X value says if your X value is less than 2, okay, that would fall in this domain right here. Well, then we use this rule up here. So we double the X and add 1. So that would be 2 times -2, and then you plus 1. So that's -4 plus 1 is -3. So the function for -2 is going to give you -3 as an answer. Okay, and so then we could say, okay, let's do f of 4. Okay, so the same function, f of 4. Again, I don't know why I'm writing something weird. Okay, so f of 4. Well, let's read the ifs. Okay, that falls in the second grouping. Why? Well, because this input value for X, if your X value is greater than 2, well, that's 4. 4 is greater than 2. So if your X value is greater than 2, well, then you take your X and subtract 4. Oh, look, I get 0 as an answer. Okay, so using this function, you would say, well, what answer would I get? And you have to read the if to say which one applies to it. Okay, and read the if on the right. So now here is a visual of it. Okay, and they're saying, okay, well, I want you to use the graph. So this is a different question, but they're asking the same things of it. Okay, so I want you to look at this graph here and notice it does pass the vertical line test. Every vertical line you could draw gives you a specific result. So let's talk about it. Okay. So if you look at this picture, I'm going to ask you a question that we don't have. If you have X is 0, okay, what is the output for X is 0? When you go to X is 0, it looks like it's -1. Okay, so I could write this as f of 0 gives you -1. You see that? If you say, okay, what was the result if you do this function and you plug in, say what they say, -2? Okay, so you go X is -2 and you see, what did they get? Oh, it looks like, which one did they got -1, 2, 3, 4, -4. You're only going to get one answer. Don't give me more than one answer. So let's evaluate this function for something else. Let's evaluate for f of 4. So that means go to 4, 1, 2, 3, 4. And if you plug in 4, it looks like the resultant y value is going to be -3. So every input is going to have an output. You just have to go to that point on the graph, say, go to the X value and see what is the resultant answer for Y. Okay, so the way that we actually would graph this would be, you have to read the ifs and you graph those values. And so it's a little weird, but you can actually do this fine. Okay, but you just have to know how to read the if then statements. And that's one of the reasons why you take geometry before you do this. You're like, okay, I've got a piecewise function that's going to have 2 pieces on it, and it looks like they're both lines. So it's kind of like y equals x minus 3, that's a line. Y equal 2x, that is a line. So you have to say, I'm going to have 2 different lines here, but they're not going to overlap. They're going to make a function. Okay, each input is going to just have one output. And so if you say, okay, this says if x is less than or equal to 1, okay, we're going to do that function. So let's start with that one. So if x is less than or equal to 1, so let's start 1 and give some values. Always start with that beginning value, okay? And then we say, okay, and then we say less than 1 would be 0 and -1 and -2. Give some examples, but start with that beginning value. And then you say, okay, let's try plugging those in here and see what the resultant answers would be. So if you plug in 1 minus 3 is -2, and you plug in, say, 0, you get -3. Plug in -1, you get -4. And then plug in to the top function, -2 and -3 make -5. So if we graph this, it says for your function values, for x values that are less than or equal to 1, you're going to get this graph. And so we go here and we say, okay, 1 is -2, okay. 0 is -3, okay. -1 is -4. -2 is -5. Okay, so, and it keeps trucking that direction. Now notice it stops here, doesn't it? This graph includes the domain values of x is 1, and when you plug in 1, you get -2. So this graph is only defined, the top graph is only defined for the x values that are less than or equal to 1. Okay, so notice this graph is to the left of 1 for x. And notice, if you look at the equation, it does model y equals x minus 3. So notice it starts at -3 and it goes up 1 over 1. It just stops. It only is graphed for the values until x is 1. Okay, so the equation that you see is true, but it's a piece of that whole function. Okay, the next graph we're going to do, we're going to say, okay, this applies for x greater than 1. Now you always plug in that fence value, that transitional point, to both functions. So you do plug in 1 here, but when we graph it, it's not actually a member of this. We're going to make an open circle here so that we have a function when we graph it. Okay, notice x doesn't necessarily belong in it, but we plug it in to see what we'd get, so we can put an open circle there. So 2 times 1 is 2. Plug in x values that are greater than 1, so like 2, 3, and 4. So 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8. So 1, again, is 2, but it doesn't actually belong to the set. We're going to put a placeholder of an open circle there. Okay, so it doesn't actually belong to the set, but it's kind of like close to that value. 2 happens to be 4, 3 is 6, and so on and so forth. So the pieces that belong to this one would be the graph of y equals 2x. So if you extend this graph, okay, here's a hint. Notice if you extended it over here, you would get y equals 2x plus 0. Do you see how you start at 0, go up 2 over 1, up 2 over 1? If you would hypothetically look to see where would it cross the y-axis if I would extend this graph. So it is truly the graph y equals 2x plus 0, but it's only graphing a portion of that graph. Okay, so that's something that we can look at. Okay, so it's a piecewise function. It's defined for all the values, and each value just has one result. Okay, so it is a function. So let's look at the next graph. Okay, so if you were in class, I'd be like, okay, let's try this, see if you can do it. And so you got to hear the if then. Again, that's why we take geometry before we take this class, is because you have to be able to hear the ifs. Okay, so your function, your output is -3 if you plug in x values that are less than 2. Okay, so let's try that. Okay, so we make a table. You're like, okay, let's try this. So if we plug in x values that are less than -2, so we do plug in -2, but we make an open circle there because it's not officially a member of the set. But if we plug in x values that are less than -2, what is our output? What is the function going to give us? Well, -3. Okay, what if you plug in another value that's less than -2? -3, -4, -5, -6. Okay, so let's see. At this point, I'm going to pause a half second. Sometimes people are like, why aren't we shading on these? I see lesson signs. I'm like, no. Shading is when we've got y is less than or equal to 2x plus 3. Okay, and we graph this line and we graph above or below it. That's not what we have. We have f of x equals. These are specific values that we're getting based on these functions. So we're not shading. We're talking about an x value between things. So we're inputting x values in a range from a domain, and we're getting a certain range values as a result. Okay, so we have an equal sign for a function. So the answers to our function are going to be specific numerical values. It's not a less than or greater than a value. Okay, so if we plug in x values that are less than -2 from that domain, we're going to always get -3. So no matter what you plug in that domain, your result is -3. So we're going to get a horizontal line. So if you go to -2, you get -3. And that is not a member of the set, so we'll just graph an open circle there, but everything else that you plug in there gives you -3. So plug in -4, you get -3, -5. So if your x values are less than -2, you always get -3 as a result. It's a pretty easy one to do, just sometimes kids get a little scared. Okay, the next part is going to be, okay, we're going to get a line. Do you see how that's going to be a slanted line? So y equals x minus 1. And we're going to graph that line between -2 until 3. Okay, so let's make our domain. So for the domain values from -2 up to 3, you're going to plug in -2, -1, 0, 1, 2. We're going to plug in 3, but we're going to make an open circle because 3 is not officially in this group. Okay, -2 is, but 3 is not. And so when we plug it into this function to say, okay, what would we get as a result? We use the second equation to say, okay, we take x and subtract 1. So if we plug in -2 and subtract 1, you get -3. Plug in -1, you get -2. 0 is -1. 1 is 0. 2 is 1, 3 is going to be 2. So if we graph these, we're going to graph the x values between -2 and 3. So at -2, we get -3. Now notice it fills in this dot. Sometimes they connect cutely. Okay, so if you're programming and you're making shapes, sometimes you want them to connect. So this one does connect. It fills in the dot. So go ahead and fill it in. You don't have to make it open, close at the same time. It actually just fills it in. You complete me is what I sometimes say. I'm like, okay, it fills it in. So -1 is -2. Cute. 0 is -1. 1 is 0. 2 is 1. 3 is 2. Okay, and it's an open circle there. So it's between here and here. Notice, if you look at the graph, it is y equals x minus 1. So you start -1, go up 1 and over 1. Okay, so that is the graph. And it's graphed from when x is -2 until when x is 3. Okay, and then the last one we're going to do is we're going to say, okay, the last one involves x domain values that are going to be greater than or equal to 3. So you start at 3, but we'll fill that in, and 4 and 5 and 6. Okay, so let's do this. So you double your x and add 1. Okay, so if your x values are greater than or equal to 3, we use that last rule. So double your x, so 6 plus 1 is 7. 4 times 2 is 8 plus 1 is 9. 5 times 2 is 10 plus 1 is 11. And then we're going to get 13. So we can graph these. 3 is 7. And again, we're going to fill this in because 3 is a member of this domain. 4 is 9. Okay, and so we're going to say it goes this way. So notice this is y equals 2x plus 1. Now, it doesn't start at 1. It starts at 7 here, according to us. But if you extended this line, you would notice it would hit the y-axis at 1. Okay, so it's really that graph, but it's just graphed with a slope of 2 starting at 1, but you only graph the portion of the graph when x is greater than or equal to 3. Okay, so it's kind of a weird concept, and so you have to practice it. And so if you read this next problem, you'll notice that we're talking about if you order this much stuff, it's going to cost this value. Okay, so if you write a function, you always start with f of x equals, and then you write your functions, you tell the ifs, the domain values for which this applies. Okay, so your first part says, hey, it's going to cost you $88 per jersey if you order fewer than 5. Okay, you could say greater than or equal to 0, yes, because, obviously you're not going to get negative jerseys, but if it's in context, it makes sense to do either way. Okay, and so how much is going to cost you if you do from 6 to 11? Okay, so it's going to cost you $75. So if x is less than or equal to 11, but greater than or equal to 6, okay, and again, we're not going to order 5.5 jerseys, that's just weird, okay, and then it's going to cost you $65 if you order between 12 and 29. That's a 29. Okay, 12 and 29. And then the last one is $56 per jersey. It's cheapest if you have a big order because they've already set up machines. They just say marks that go. Okay, so if x is greater than or equal to 30. Okay, so you've got to define the parameters. Now, it's not a slanted equation, y equals mx plus b. However, it's like a specific output value for these things. Okay, so when we look at a graph, I want us to kind of think about how could you write these equations? And so we're going to start with lines, okay, because you guys know lines. We're going to do y equals mx plus b. So the y you start with is always f of x equals. And so I want to see that. And I want to see, okay, so do that. Okay, so we've got two equations. And the thing is, y equals mx plus b is true, but you have to make sure b is not the beginning value, b is the y-intercept. And so you might have to extend your line so you're smart like that. And so your first equation is y is equal to, so f of x equals, that counts as y equals, and that's going to be a half x, and that's plus 1. Notice it hits the y-axis at 1, okay? And that is if, okay, what domain values does this do? Okay, that is the domain values if x is less than or equal to 2. Okay, so you're graphing that line if your x, oh, it's not less than or equal, it's less than, isn't it? You see how it's an open circle there? Now, we've got another line, okay, and that's if x is greater than or equal to 2. Okay, so if you plug in x values, then there's another line. Do not fall in a ditch. The slope is 1x. Yes, that's true. Okay, but what is the y-intercept? It's not -2. You have to be a ninja, okay, and say, okay, let's go down here. Oh, it crosses at -4. Okay, so you're graphing the line y equals x minus 4, but you're going to graph it only the portion of the graph if you plug in x values that are going to be greater than or equal to 2. So try your delta math. Don't throw your computer against the wall, okay? But the truth is that I want you guys to practice evaluating these functions. I want you to practice graphing them and see what you can get. See how you can grow with this practice. Good job. Thanks. Bye.